Good morning, good afternoon, and good evening. Thank you for joining Airflow Day 2022 on Google Open Source Live. If you haven't attended Open Source Live before, it's a monthly web series where each month we explore a different topic within open source. Today, of course, is all about Airflow. My name is Leah Cole, and I'm a developer relations engineer working on Cloud Composer, Google Cloud's hosted, managed Apache Airflow. My title means that I'm a software engineer, but instead of building the end Composer product, I build tools and resources that help make it easier for other folks to use Composer. And today, I'm joined by my co host, Frank.
Hey, thank you, Leah. Good day, everyone. My name is Frank Guan, and I'm a product marketing manager for data analytics at Google Cloud. I'm really excited to co-host today's amazing event covering all things Airflow. Leah, can you please tell the folks what's in store for today?
Totally. We have some really interesting topics on our agenda. If you're looking to learn more about Airflow, you are in the right place. To start, I'll actually be leading a session. My session's called Happy DAGs and Happy Teammates, How a Little CI/CD Can Go a Long Way.
Oh, I love it. Well, before we get started, folks, don't forget to put your questions in the live Q&A forum below the live stream window. Speakers are ready to answer your questions live, and we'll get to as many as they possibly can within the time allotted. Just a note, if you're viewing in full screen, you'll need to exit full screen to see the live Q&A forum. Our sessions have been pre-recorded to allow for accurate transcript and so that speakers can focus on answering these questions live. Once we're done, don't forget to join us at the after party. You will see a button to join the event page at the end of the last session. Oh, and last but not least, use the hashtag GoogleOSLive to share your experience on social media. With that, let's get started, Leah.
Hi, everyone, and thank you for coming to my session, Happy DAGs and Happy Teammates, How a Little CI/CD Can Go a Long Way. My name is Leah, and in addition to being one of your MCs, I'm also a speaker today. I'm a developer relations engineer at Google Cloud, which means I'm a software engineer by trade, but instead of using those skills to build the end products in Google Cloud, I build tools and experiences that make it easier for other software engineers to use Google Cloud. My day-to-day varies, but it usually means doing things like writing sample code or tutorials, sometimes blog posts, and talks like this one. My focus is on Cloud Composer, which is Google's hosted managed version of Apache Airflow. In this talk, I will be focusing on Composer, but most of what I say will be able to be translated to other forms of Airflow as well. I'm an Airflow committer. I've been involved in the project since 2018, and one of the ways I stay most involved is as an organizer for the Airflow Summit, which just happened this past May. I would encourage all of you to check out the talk replays at airflowsummit.org and to keep an eye out for future events. And a fun fact about me, I love yarn crafts, I knit and crochet, and I love cats. I have two cats named Millie and Frank. All right, I know I can't see you, but if you could raise your hand along with me, if you've ever had a DAG that worked locally, but not when you deployed it, or maybe you've completely lost track of what you have and have not tried to make a DAG work. Maybe you've just seen the big red broken DAG error in Airflow. Or maybe you looked at Airflow and realized that the changes you made 3 days ago never actually got deployed to your environment. I'd say that these are situations where you're dealing with unhappy DAGs. You were probably unhappy, and if you have teammates, they may have been unhappy as well. And these are situations I have been in, all of them. The good news, though, is I do have some solutions I'd like to propose, and we can talk about putting them all together to hopefully make sure that we can greatly reduce the level of that unhappiness when working with Airflow. So let's start with that first problem, the classic stepping stone of every engineer, the "it works on my machine" problem. Let's say you work in a shared team Airflow environment, but you do most of your work locally. And when it comes time to push your work to deployed Airflow, something in the DAG's just not right. I think this happens fairly often. Airflow is pretty complex, and it has a lot of ways that it can be configured. We have all these connections that we have to manage. You're dealing with things like permissions, environment variables, configs that you can override. It just has a lot going on. The good news is I think there's a solution for that, and it's having multiple airflow environments. So in other types of software engineering, we have multiple environments to ensure production stability for our end users. We should be doing that for our data pipelines too. At minimum, I recommend 2 airflow environments in addition to whatever you're using for your local environment. And I'm going to call them dev, development, and prod, production. You know what works best for your organization in terms of naming, or if you want to have more than that. But the one caveat I'll say is the more you have, the more you have to manage. So let's talk about this potential 2 environments plus local dev scenario. You have your local environment. Maybe you're using something like Airflow Breeze. Maybe you're just running your own version of Airflow on your computer, whatever works for you. This is your environment. It's your sandbox. It's your playground. You can do whatever you want here. This is where you experiment and figure out all of the things with your DAG, at least as you're starting out. And once it's in like an okay-ish state, or where you're going beyond the capabilities of your local environment, you'll use that dev environment. This is where you can deploy DAGs if you need to work on them in a more realistic environment. Though if it's shared, be considerate of your teammates, and if you think that you're going to be making a mess, at least give them fair warning. You can debug your DAGs here because the configuration of this environment is going to be really similar to the configuration of your production environment. It's going to have the same version of Airflow. It should have the same version of Python packages. It should have the same plugins, and it should have the same types of connections. You should not actually have connections to your production data sources, but let's say that you have a connection to AWS in your production environment. You should also have a connection to AWS in your dev environment. The dev environment is also where you can do things like test out changes to the environment itself. Like if you're not sure what a new version of Airflow is going to do to your DAGs, if anything, this is where you'd try it out before putting it into production. The thing I recommend with your development environment, whether you're by yourself or with a team, is to keep a change log where you track what you do to the environment or what you're doing to debug your DAGs. That way, future you can learn from yourself, and future teammates and current teammates can learn from you. Now, finally, we have your production environment. This environment is tightly guarded because it's where your production pipelines run. You should do things like practice the principle of least privilege and only deploy DAGs here that have been thoroughly vetted and tested both in your local environment and in the development environment. Be strategic about when you put your DAGs in this environment. Is there a good time of day for things to go wrong, or at least awful time of day? That's probably when you should do your deployment if you can. And last but not least, you should have a rollback procedure in place. We're human, humans make mistakes, and also sometimes weird stuff happens with technology. It's much better to have a plan in place that you can follow before you need it. Okay, feeling a little happier now that we have those multiple airflow environments. But now, okay, what if you have a problem pipeline and you've tried a bunch of different things and you can't remember what you've tried and it's just not working, or like a DAG suddenly breaks and you go to fix it and you're like, oh man, I've had this problem before. I had to do it a few months ago. I don't remember what I did. Or, and I see this one a lot. You inherited a DAG from someone that you now maintain, and that someone is nowhere in reach, and you have no idea why this DAG is the way it is. This happens. The fix, though, I think, is version control. It's best practice to use version control to keep track of your production code. Teams want to be able to see when you made changes, what changes you made, who made them, and why. Doesn't that seem like info you'd want to have about your DAGs as well? There's no reason not to treat the DAGs like their production code, even if you work by yourself. So I have a proposal, 2 version control flows for you. One if you work by yourself, and one if you work in a team. So your solo flow, pretty simple. Make a commit, but give it a detailed message, not just like test. And then you push your changes to a branch. That commit message is a gift to your future self, and you'll thank your past self later when you read it. If you're on a team, pretty similar. Make a commit, again with a detailed message. You open a pull request, have your teammate review it, and then you merge those changes into your branch. Okay, feeling a little happier. We've got our version control, we've got our airflow environments, multiple, but what about the broken DAG error? Well, obviously, the solution is just fix your DAGs, but no, let's see, what can we do to reduce the number of times we have broken DAGs in the first place, besides using version control in multiple airflow environments? We can test them. But how? Okay, I'm not going to tell you exactly how because there's a lot of different ways that you can do this, but I am going to tell you a few of those ways and provide links to some resources. And these slides will be available afterwards, so you can click on each of these links. So we test other production code before submitting it. Why not also do it with our DAGs, especially when there are so many resources for us to use? You can use the Airflow CLI or write a package that checks for syntax errors or task errors. You can write unit tests, and you should especially do this if you're writing custom hooks or operators. You can also do it to validate your DAG structure. In Airflow and in the provider packages, all of the operators and hooks do have unit tests, but if you're writing your own, this is where you definitely want to do it. You can run your DAGs in your local environment, or you can run them in your dev environment. And these are some testing resources that I was talking about earlier. There are some that are from Google, some that are from Astronomer, some that are from past Airflow events and blog posts. And who knows, maybe after this, you will learn so much about testing that you will write a blog post about it. And if you do, please share it with me. I'd love to read it. All right, we're testing our DAGs. We're using version control. We have multiple Airflow environments. What about the very human feeling of realizing you forgot to deploy the changes you made a few days ago? There's a fix. It's automation. In my lightning talk at the Airflow Summit in 2021, I told folks robots are your friends, and I stand by this. And this is an excellent use case for automation. Why would you rely on an unreliable human to do something that automation can do much more reliably and consistently? With tools like Google Cloud Build or GitHub Actions, you can make sure the most up-to-date version of your DAG is in your Airflow environment. And you can do it when certain conditions are met, either when there's a change to that DAG, or you can just do it at a certain time interval, like every night you sync your DAGs with your environment, whatever makes most sense for you. So now that I've talked about these 4 things on their own, let's examine a combo of them in practice. So let's say I want to make a change to my DAG. I open up a pull request and it triggers some unit tests that I have running in Cloud Build. These unit tests check my DAG structure. They make sure it's valid and there's no cycles in it. My teammate reviews my DAG, and when they're happy with it, we merge it into our main branch. Once it's merged into our main branch, a Cloud Build automation job copies that DAG into my development composer environment. And this is where me and my team do our Airflow work together. Once it's there, I can take a look at it. And if the DAG fails, I'll address those failures, open up another pull request, and do those first few steps again. If it passes, then I will manually promote that DAG to production at an agreed upon time with my team. Now, you could automate the promoting to production job, but I personally prefer not to do it because I think it's good to have another human manual step of auditing. So the 4 components we talked about today. There's multiple Airflow environments. There's a development and a production Cloud Composer environment, and what's not pictured is the local development environment where I did a lot of my work. We have version control. I'm using GitHub with my team to keep track of the changes in my DAG. We have DAG testing, both in pre-submit unit tests that are triggered during my pull request and in the actual manual running of the DAG in a development composer environment. And we have automation, both in those pre-submit tests and in the copying of the DAGs to our composer environment. So now I have a quick demo for you where we can see what this looks like in action. All right, so here is my composer Airflow environment. We can take a look. I have this one DAG here, and all I'm going to do is I'm just going to add a comment above this first import to show this flow. So this is the storage bucket where my DAGs live. We can see it was updated at 3:25 p.m. I'm going to make a change in GitHub using the UI, where, as I said, I'm just going to add a comment right above that first import. I'll use the UI to create a pull request with a helpful description, following that nice little solo flow. And then I'll open a pull request. This will kick off automated unit tests running in Cloud Build. And if we go to the Cloud Build UI, we can see the test DAGs job running. It has a few steps. It installs requirements, and then it just runs unit tests that check the validity of my DAGs. So once they pass, I can pretend to be my own reviewer and go approve my pull request and merge it. And then that will kick off another Cloud Build job. So back in the Cloud Build UI, we can see this job is called Add DAGs to Composer, and it just has 2 steps: installing requirements and executing a Python script that copies DAGs from GitHub to the cloud storage bucket associated with our environment. That bucket I showed you earlier. That bucket previously said it was updated at 3:25 p.m. But if we take a look at it, we hit refresh, we can see it was updated at 3:31. So there are new changes in there. And then we can go back to our Composer environment to Airflow. And if we refresh, we should see our test comment is right there, working exactly as we hoped. All right. Thank you for joining me here today at Airflow Day. I will be answering questions during the live Q&A, and here are a few other resources for the slides and for other Airflow information and tutorials about how to run this flow. Thank you again for joining me.
Thanks, Leah. I've certainly learned a few things about the best practices of dealing with these DAG common scenarios myself. Thanks for telling us about how to make your time using Airflow a bit happier. Next, we'll hear from Sławek, who will be discussing how Cloud Composer integrates with Airflow role-based access control. Take it away, Sławek.
Hi everyone, my name is Sławek. I'm a senior software engineer at Google, and today I'm going to talk about the integration of Cloud Composer with Airflow role-based access control. So why am I here and why this topic? I'm a tech lead in the Cloud Composer team, and Cloud Composer is a cloud service that hosts Apache Airflow software in Google Cloud Platform. So we have quite some experience with Airflow in our team. What's at the core of my presentation is answering this question: how extensible is Airflow when it comes to its access control model? In particular, I would like to show how we can integrate it with Cloud Identity and Access Management, or Cloud IAM for short, and how we can automate Airflow access configurations. But first, a few words about Airflow role-based access control itself, or Airflow RBAC for short. Airflow RBAC is a model built into Airflow that allows managing permissions, users, and roles in Airflow UI and Airflow API. It is based on Flask App Builder, which is the underlying framework for Airflow RBAC UI. It basically allows configuring which users can see what pages and what DAGs in Airflow UI, or access them through Airflow API. Note that Airflow CLI, the command line interface, does not respect these settings at the moment. You can also access the whole metadata database directly from your DAG code anyway. But in Airflow UI and API, it works. The screenshot on the left shows how permissions are grouped in a role, and the screenshot on the right shows how roles are assigned to a user. So how does Airflow RBAC look like in Cloud Composer? When you create a Cloud Composer environment with Airflow 2, Airflow RBAC UI is enabled by default, because that's the only kind of UI available in Airflow 2. And you can see in the top right corner that you are automatically logged into Airflow UI after you pass the Google authentication. The overview of the integration setup is presented in this diagram. There are 2 layers. First, you reach a Google proxy, you authenticate with Google, and your permissions are checked in Cloud IAM, in the cloud project of your Cloud Composer environment, to verify that you can access the given instance at all. Once you pass this step, you don't authenticate again, more on this later, but now Airflow checks your permissions to specific Airflow views and DAGs based on the configuration stored in the Airflow metadata database, which is how it's been originally implemented in open source Airflow. How to configure access to Airflow UI and Cloud Composer? First, the user must be granted access in Cloud IAM. That's the first layer from the previous diagram. For example, Composer user role contains the necessary permission. Then, the user must be granted access to specific views and DAGs within Airflow RBAC UI. For example, An admin role is good for, well, admin users, as it contains permissions to all views and DAGs. But how are users registered in Airflow RBAC? When a user visits the Airflow RBAC UI instance for the first time, they are registered in Airflow RBAC automatically. Their email address and user ID are stored in a new record added to the Airflow metadata database. The default role with which users are automatically registered in Airflow RBAC in Cloud Composer is op. But this default can be modified by setting the RBAC user registration role property in the web server section in Airflow configuration override settings of the given Cloud Composer environment. You can set this property through Composer API, Composer user interface in Cloud Console, or gcloud command line interface, whichever way you use to interact with Cloud Composer itself. There is also an option for administrators to pre-register users by their email addresses manually. They are then resolved to user IDs at user login time. This is useful for assigning roles to users before they log in, because a user record must be created in Airflow metadata database before roles are assigned to the user. Now, let's dive into some details of how we adjusted Airflow to make this seamless integration possible. Airflow is already integrated with Google Authentication, but the problem we faced was that users would be greeted with two authentication requests, one from Google Proxy and one from Airflow UI. That's no good, but thankfully we managed to eliminate the need of the second sign-in by making use of user identity passed from the proxy in a signed header. The header contains a unique stable identifier of the user and their email address. They can be used to register or log in the user into Airflow UI. And that's exactly what we did by implementing a custom login handler in the Airflow web server. The handler decodes user ID and email address from the header, looks up the user in Airflow RBAC tables in the Airflow database, and if the user has been pre-registered with an email address, updates the records with the user ID, or if the user doesn't exist, it creates the new record in the database for this user. And finally, the handler logs in the user. Looking into the code, the implementation is actually pretty clean here, as Airflow web server is ready for such a customization. All we did was providing custom auth view and Airflow Security Manager implementations, which include the login handler logic that I just described. And then we set them in the common webserverconfig.py configuration file. And voila! A user is registered and logged in automatically with no need for the redundant second sign-in step. But when it comes to interacting with Airflow Access Control, we didn't stop there, and to further improve the experience of configuring access control in Airflow, we proposed a feature called per-folder roles registration. What problem does it solve, and what does it actually do? DAG-level permissions are an important part of Airflow RBAC. They enable limiting which users see which DAGs in Airflow UI. Adding per DAG permissions to roles can be done either by editing roles in Airflow UI or by specifying roles and permissions through the access control property in the DAG code. This is shown in the screenshots. And this works, but what if you have many DAGs and many roles to which you want to add the per DAG permissions? In that case, maintaining a consistent configuration can be cumbersome and error-prone if it depends on manual configuration of every single DAG. This is a problem that we've identified and wanted to solve it through automation. But how can we automate assigning DAGs to roles? This is where we came up with the idea of per-folder roles registration. In this approach, DAGs are naturally grouped by subfolders in which the DAGs and their files are defined and where they are located in the file system, or in subfolders in Cloud Storage Bucket in case of Cloud Composer, because that's where you put your DAG files when you deploy them in Composer. Then we can use the subfolder names as role names, create the roles in Airflow RBAC, and populate them with edit and read permissions to the DAGs which files are located in this subfolder, all automatically. This is pretty clean, and it automates the DAG to role assignment. How did we implement it? We used another Airflow customization mechanism called cluster policy, which enables you to inject code to execute in the context of parsed DAGs or tasks. Here we operate on DAGs, so we define the DAG policy in the standard Airflow local settings.py file. This policy has just two steps. First, it extracts the role name from the DAG file path. I didn't include the implementation of the role from file path function in this slide, but you can imagine it's pretty simple. Then it merges the new per folder role and permissions to this DAG with the additional DAG access control settings specified by the user in code, if any, because they are completely optional now, thanks to this automation. This way, both become effective, and that's it. In the recent versions of Airflow 2, settings from the modified access control property are automatically synced to our Airflow RBAC tables. Admittedly, we also needed to add a couple of small patches in other places of our Airflow codebase to improve handling certain scenarios, like when a DAG is deleted. But hey, with open source code, that's easy too. We added the per folder roles registration feature to Airflow instances available in Cloud Composer. You can simply enable another Airflow configuration override in Cloud Composer environment settings. It's called RBAC autoregister per folder roles in the web server section, and you can set it to true either through Composer API, Composer user interface, or gcloud command line interface, again, whichever way you prefer. And then you're good to go. The feature is enabled for you, and you just put your DAGs, your DAG files into subfolders, and the structure is automatically mapped to roles with per DAG permissions assigned to those roles. This way you can, for example, streamline the scenario of multiple groups of people in your team working on different DAGs, so that each of them can only see the DAGs relevant to them, effectively decluttering the view in Airflow UI. To summarize, I believe we demonstrated that Airflow is extensible, also in the more advanced area of role-based access control. We integrated it with cloud identity and access management in some form, and further extended Airflow access control with per folder roles registration mechanism. And that was without deferring to many hacky patches, but rather using the available configuration and customization mechanisms. If you want to learn more about Airflow UI access control and its integration with Cloud Composer, please check out the Airflow documentation and Composer documentation as well. Thank you for your attention. It's been a pleasure to speak at this event, and I hope you learned something today. Thank you.
Thanks, Sławek. It was great hearing about Composer's integration with Airflow RBAC. Okay, next we'll hear from Mateusz, who will be highlighting user code isolation in Airflow. Take it away, Mateusz.
Hello everyone, and welcome to my presentation. Let me start by saying just a few words about myself. My name is Mateusz Hens, and I have been working for 5 years at Google. Last 2 years I spent as a senior software engineer in Cloud Composer team. Today, I would like to share with you some information about the efforts that Cloud Composer team is involved in Airflow community. As you can see on the screen, they are connected to isolation between user code and Airflow code, which we see as a problem in existing Airflow architecture. Let's start, and before we get to the solutions, let's take a look at how Airflow is set up today. What you can see in this slide is a very simplified architecture of Airflow that is used in Cloud Composer and probably in many standalone Airflow installations. I focused only on the most important components to make the picture as clear as possible. Airflow itself runs 3 different types of components: scheduler, worker, and web server. Scheduler is responsible for parsing DAG files containing the user code, putting them into the database, but also it runs another process called scheduler job, which is responsible for scheduling the tasks for execution. So it checks all dependencies for a task, like time, parent task state, and if they are all met, it sends the task for execution by putting them in the Celery queue. Celery queue, which is actually not a part of Airflow code, but just external component, and it's just a broken between 2 components, as on the other side of it we have Airflow workers. There may be many of them. In Cloud Composer 2, the number of workers is automatically scaled for you based on the number of incoming tasks. Each worker has some number of slots which controls how many tasks can be executed in a single worker in parallel. If you take, for example, 6, then single worker can take up to 6 tasks from the queue at the same time. If all workers are occupied and setting for maximum number of workers doesn't allow our autoscaler to scale up, then tasks are waiting in the Celery queue for some free slots. Airflow uses database to store its internal state and task and DAG execution history. Components simply write and read data from it during their execution. Users are able to upload their code to DAG as DAG files using Cloud Storage Bucket. Components that need these files for execution, like worker or scheduler, sync their local storage with the bucket content. And finally, we have Web Server or Airflow UI, which allows users to see and manage DAGs and tasks with a nice user interface. In our customer cases, we see that some patterns occur more often than others. So we notice actually some flaws in this architecture. First of all, as I said, all components have access to the database. It must be open and accessible by every single worker, scheduler, web server, process running in Airflow installation. Usually, it requires root access on the database. So the problem is, the code executed in scheduler on worker is a user code, which means user is able to run any SQL query on the database, including deleting tasks, even unrelated, locking the database rows, or even the whole table. Believe me or not, we got few cases from our customers where the whole database got locked by some not well-written DAG. Secondly, I mentioned that scheduler has 2 processes. One for parsing DAGs, second for responsible for task scheduling. In Airflow 1, they were coupled more tightly. However, thanks to great work of community for Airflow 2, these 2 processes can be split and run independently. Some of customers encounters the problem when with many DAGs, the DAG processing process of Airflow scheduler starves the scheduler job. As the result, tasks are not scheduled or scheduled with a delay. Thirdly, long-running worker with a dedicated number of slots is nice from performance perspective. Usually, there are some free slots ready to pick up the task as soon as it appears in the queue. But it also means there is no isolation between them. Tasks from different DAGs are executed on the same host without any sandboxing, and they share the same resources. You can imagine the problems like one task failing with out of memory, and it crashes all the other tasks that were just unlucky to be scheduled on the same worker. Another problems are PyPy dependencies. 2 tasks may require some external dependencies, which may conflict in many ways. Finally, user Python code provided as DAG file is fetched and executed on workers and schedulers. As it is Python, then everything is dynamic. Means the code is able to even change the Airflow code, install dependencies on the fly, and of course leaving this mess afterwards. It also has another problem. All code is stored in a single location, which makes it hard to, for example, share the instance even between different team members, for example, for development purposes. So just to summarize the problems, there is a direct access to the database for all the components. There are components running both user code and Airflow code with the same privileges. There are different tasks executed on the same worker. Actually, the same applies to DAG processing. And there is a single location for all DAG files. So yeah, Airflow has its problems, but of course, each challenge is an opportunity. Before we move to the solutions, I would like to briefly describe the high-level idea. We found that we can split components into two groups, trusted and untrusted. Components should be considered trusted if and only if executes Airflow community code. This code is checked during the code review process, also tested during the release preparation, and in Google we can run it through our security review before we add it to Cloud Composer for our customers. It also means no custom PyPy dependencies or plugins, just to make sure the code that is executed here is fully auditable, which of course excludes even accessing the DAG files in any way. And due to that fact, we can audit the code, so we are sure what kind of DB access or what kind of DB queries are executed here. So trusted components may keep the direct connection to the Airflow database. On the other hand, we have untrusted components. They execute the user code either from DAGs, plugins, or PyPy dependencies. However, due to that fact, the access to the database should be limited and possible only through some API. When we approached community about these problems and ideas, we quickly learned that they share the same concerns. We decided to work on fixing this issue in Airflow community and merge all our changes there, so not only our customers can benefit from them, and we can still keep 100% compatibility with Airflow in Cloud Composer. We learned that the ideas that we had fit well into the Airflow multi-tenancy effort run by the community. So far, we prepared two AIPs, Airflow Improvement Proposals, that you will learn about in a minute. Let me start with AIP 43 about DAG processor separation. This AIP is about separating the DAG processor process from Airflow scheduler and running it on a standalone host, different from scheduler job. As a result, the DAG processor can no longer affect scheduler work or vice versa, that we see now if Airflow is overloaded. And most of the work is already done. In Airflow 2.3, it is possible to run independent DAG processor. Even though the change looks simple, it requires some refactoring. For example, scheduler job and DAG processor exchanges information about callbacks through multi-process pipe. Callbacks are just some functions defined by the users, which should be executed on some conditions, for example, DAG or task failure. Of course, when scheduler and DAG processor are executed on different hosts, then multi-process pipe can't be used. Instead, we decided to use the database as our queue for callbacks, with one component writing them to the new table and the other reading and executing. So in Airflow 2.3, we can run independent DAG processor. As a side effect, scheduler job, named Airflow scheduler in this picture, no longer needs to sync DAGs from the bucket, as it no longer operates on any user code. It means that this process fully meets the definition of trusted component. Of course, DAG processor separation is an opt-in feature. To use it, you need to configure your Airflow instance. Please see the AIP 43 for details. I mentioned that this AIP is almost ready. So the only remaining part is possibility to run multiple DAG processors, each parsing DAGs from different locations. This could be used either to separate the DAGs that are heavy or slow to parse from others, maybe production critical, or separate them by teams or developers. I can also imagine that in the future, each DAG processor may use different service account and set of PyPy dependencies. But please remember that workers are still shared, so some more work is needed here as well. Second AIP is about solving the direct access to the database. Again, if you need more details, please check the AIP 44. We can see on this picture the two components that are considered untrusted. So we have a DAG processor and Airflow workers. They execute the user code, but still have access to the database. And this is a dangerous habit we want to finally break with. The idea for this AIP is to introduce new component called internal API. It exposes a limited number of operations that can be executed on the database. And this is fully trusted component running only Airflow community code. DAG processor or worker can no longer connect to the database directly, but they can only make calls to this internal API. The requests are, of course, translated to the SQL query and executed on the database, but the code of this internal API is reviewed by Airflow community. And of course, the list of methods is strictly limited to only what is needed by worker to run. So dropping the table or database is no longer possible. There is still one problem with authorization. A particular task or DAG should be able to change only its own state and have limited access to secrets or connections. In the first phase, we plan to do simple check, whether the calls comes from the worker and probably with some long-living tokens. Later on, the community plans to introduce fine-grained access control, and there is a different group of folks working on that. The feature may bring some breaking changes. So for example, if user DAG or tasks depend on accessing the database, then they will no longer work. Due to that, enabling it requires changing the configuration. This AIP still needs some work. We have concept, we have ideas, but no code is merged yet. We just need to decide on some details to make sure the Airflow developer experience stays the same. And there is no need, for example, to implement the same features accessing the database twice, once in the normal mode with direct database access, and the second with database isolation mode. So these are two AIPs that Cloud Composer is working on right now. But what next? Let's look again on the architecture that I showed at the very beginning. The AIPs that I mentioned solves two problems. Airflow scheduler running two processes, untrusted DAG processor and trusted scheduler job. And second, direct access to the database for untrusted components like DAG processor or worker. DAG processor separation also partially solves the problem with a single DAG's location, as we are able to run multiple DAG processors pointing to different directory. However, DAGs from the same directory will still be parsed without any isolation of the same host. Moreover, tasks are still executed by the shared set of workers, so there is still some work needed here. What about other problems? Problem with workers running different tasks can be solved by using existing Kubernetes executor. It will create a dedicated Kubernetes pod for each task. And of course, for the cost of inter-task latency. Currently, in the community, there are some AIPs that could help there. There's an idea to introduce runtime isolation for tasks in a worker and DAGs in DAG processor by executing them in a dedicated Docker container. The image for the Docker can be defined at the task or DAG level, which actually solves the problem with PyPy packages configs. and user code executed in the same context as Airflow code. And of course, to make it fully secure, the fine-grained access control is needed to make sure worker and DAG processor can only access resources they need. We know that our journey just began, but we are looking forward to contribute in every single feature there as a single part of a bigger picture. And we are sure it will bring a lot of benefits, not only for our customers, but also for any users of our Airflow. That's all that I had for today. I hope you enjoy it. If you're interested in any of these topics, please check the AIPs that I mentioned. And remember that all of these activities take place in Airflow community. So if you would like to join and help, then you are more than welcome. Thank you.
Thanks, Mateusz. It's good to learn about the distinction between the trusted and untrusted component schedulers and how to work with each of them. Next up, Rafael will be discussing running Airflow on Kubernetes. Over to you, Rafael.
Hello, my name is Rafał Biegacz. I'm working for Google, where on a daily basis I'm working on Cloud Composer, which is a managed service for Airflow. And today I have a pleasure to talk to you about how to run Airflow on Kubernetes, either using Cloud Composer or community-baked Airflow Helm chart. So before we get to the nitty-gritty details of how to run Airflow on Kubernetes, let's maybe focus on what actually Kubernetes is. So Kubernetes is a distributed platform for running distributed systems. And it was built according to the modern software deployment paradigms, like infrastructure as a code. It has capabilities that allow you to auto-heal and auto-upgrade your application. So it's a very modern platform that is very popular nowadays. You can run it anywhere in your private data center. You can go to a public cloud and you can do self-managed Kubernetes, or you can use one of the managed services that deliver Kubernetes to you. What it promises to you is no vendor locking. It's an open source technology, and it's part of Cloud Native Computing Foundation initiative. Cloud Native Computing Foundation organization ran a survey in 2021 when they asked many questions related to Kubernetes and other technologies to the users. And one important data point from the survey is that 96% of the users either already use Kubernetes or they are planning to do that. So as you can see, no doubt Kubernetes is very popular. Okay, so now let's maybe talk about Kubernetes in the context of Airflow. There are different ways of running Airflow. You can use virtual machines. You can also again use Kubernetes, and there are some other methods to run Airflow. Airflow community ran a survey in 2020 when they asked what's the most popular way of running Airflow when it comes to Airflow users. And as you can see on the right-hand side, that Kubernetes and virtual machines are two the most popular methods of hosting Airflow environments. If you would like to learn more about the survey results and especially more how to Airflow is running on Kubernetes, you can also go and find Airflow Summit 2021 presentation called Airflow Loves Kubernetes, which has plenty of information. Now let's talk about how to run Airflow on Kubernetes, and this part of today's talk will be consisting of two phases. First, we will run Airflow on Kubernetes, and then we will focus on Kubernetes features that are very attractive for, very beneficial for Airflow. I'm going to cover two ways of running Airflow on Kubernetes. So first, we will focus on using Apache Airflow Helm chart. And in the second step, we are going to take a look how you can use Cloud Composer to run Airflow environment on Kubernetes. What is actually a Helm? Helm is a package manager for Kubernetes, one of the most popular package managers for Kubernetes. And again, this is a project that is part of Cloud Native Computing Foundation. And Helm allows you to package all the parameters required to run your application in the form of charts. So Airflow community prepared a dedicated Airflow Helm charts for Apache Airflow, so you can easily run Airflow on Kubernetes in a few steps, and we will see in a moment how easy it is. So first of all, we need to have a Kubernetes cluster. So for example, in case of Google Cloud Platform, you can navigate to Google Cloud Console, which is a user interface for that you can use to create resources in Google Cloud Platform. With a very few steps, you can, using user interface, you can create a cluster. After you provide some initial parameters, within a couple of minutes, the cluster will be created for you. If you prefer to use some other way of creating Kubernetes cluster, like for example, some command line and the gcloud, there is a way to open a Cloud Shell on GCP Cloud Console where you can enter your commands and cluster will be created for you. Once we have the cluster, now we can focus on configuring Airflow so it runs on Kubernetes. So again, in GCP Cloud Console, you can navigate to Cloud Shell. Within the Cloud Shell, you will have already Helm installed. So to be able to proceed with the installation of Airflow, you need to add Apache Airflow repository to Helm. Once you do that, in the second step, you need to run a Helm update command. Then the next two commands that are presented in the screen are related to definition of needed variables, release name and release namespace. In the fifth step, you are going to create a namespace on Kubernetes cluster within which all Airflow components will be running. And the last step in this procedure, this is using Helm actually to execute all the commands from Apache Airflow chart. And again, once you initiate this command, within a couple of minutes, you will have a fully blown Airflow environment. Maybe just one disclaimer. When you use Apache Airflow Helm chart, with default parameters, you are going to create an Airflow environment that is very good for testing out, but maybe not for production usages. Of course, it is possible to use Helm chart to create production deployments. There is even a special guide created for you. The link to this guide is presented in the slide. You can navigate to this page and learn what default parameters of Helm chart should be changed to get a production grade Airflow installation. Okay, now let's take a look how we can run Airflow environment using Cloud Composer. Again, we can navigate to Google Cloud Console to the user interface. Once you enable Composer API, you will be presented with a Composer user interface page. On this page, you will be able to find the Create button. Once you click it, you will be able to see that you can select Cloud Composer, one of the two Cloud Composer versions. My recommendation to you is to use Composer 2 version, which provides to you auto scaling and by default uses Airflow 2. If you don't need to tune anything in the Airflow environment, the only actually required parameter here is the name of your Composer environment. Once you click Create button, Airflow environment will be created within several minutes for you. So in this particular case, we used user interface to create composer environment, but of course there are other methods that you can use to create such an environment. So you can use gcloud, you can use directly API, you can use Terraform. There are also Python and Java clients, so you can create composer environments in a programmatic way. And also there are Airflow operators for Cloud Composer. So from within other Airflow environment, you can create Airflow environments based on Cloud Composer. Now, when we have Airflow environment running within Kubernetes, we can talk more about Kubernetes features that are so beneficial for Airflow. One very important piece of information that you need to know as a person responsible for running Airflow on Kubernetes is that the smallest deployable unit of work on Kubernetes is called pod. Usually you define usually you use YAML files to define how a given pod should be configured by Kubernetes. Within a pod, you can run one container or many containers. Additional assumption that Kubernetes makes when you run pods on Kubernetes is such pods can be restarted anytime. This is how Kubernetes works. And of course, when running a distributed complex system, some of the components of the system might be stateless. So restarting is not going to harm or do anything wrong to your system. On the other hand, some other elements of the system might be stateful. It means that after the restart, the component needs to restore its previous data. And Kubernetes provides to you a method of adjusting your needs and map your needs into the workload types that it delivers. So on this slide, I provided a list of components from Airflow environments. On the right-hand side, you can see Airflow components as they are configured by Cloud Composer. On the left-hand side, you can see components that I configured for you using Helm chart approach. And you can see that, for example, a queue that stores Airflow task, Airflow Redis, is here configured as a stateful set, which is a signal for Kubernetes that this component needs to preserve its state even though it is restarted. On the other hand, Airflow Scheduler is a stateless component. It can be restarted. That's why we can use deployment workload type. And Kubernetes knows that if this component is restarted, our system is going to continue operate correctly. So one highlight from this slide to all of us is that Kubernetes provides workload types to adjust definition of our workloads to the needs of the components that Airflow needs to run. Another very interesting feature of Kubernetes is Kubernetes services. We already mentioned that pods, which are the smallest deployable units of work on Kubernetes, they can be restarted anytime. As a result of it, such a pod can be assigned a different IP address. On the other hand, if you are running a distributed system on Kubernetes cluster, the components of the system, they need to know how to talk to each other. So for example, Airflow worker needs to know the IP address of Redis queue. Because this Redis pod can be restarted anytime and it can get a different IP address every time, it wouldn't work for Airflow worker. And here Kubernetes services come into play because these are the entities that can be assigned IP addresses for good. And even if pods are restarted, you will still be able to talk to Redis service, which is going to pass the traffic to the actual pod that fulfills a given function. One additional feature of Kubernetes services is that it can load balance the traffic between more than two pods. So for example, if you come to a conclusion that you need more web servers to be able to handle more users in your Airflow environment, you can have many Airflow web server pods sitting behind web server service. And in this way, you are going to increase the capacity of your system. So one important highlight from when it comes to this feature is that Kubernetes services give you this feature of having a permanent endpoint to the components of Airflow environment. Another very interesting feature that Kubernetes offers to you is Kubernetes secrets. So in any distributed system like Airflow, definitely you have parameters that are sensitive and they should not be exposed in a clear text to, for example, users or other components. And here Kubernetes secrets come into play because you can store all those sensitive parameters in secret vault, where those parameters will be encrypted. And they will never be exposed to users or Kubernetes pods in a clear text. When a given component needs the given parameter, they can contact Kubernetes secrets, read it out from there, and they don't need to even store this parameter within their process space. One example of such a parameter that is very sensitive is Fernet key, which is an encryption key for encrypting connections. So as you can see on my right-hand side, where there is a list of secrets, that Fernet key is stored in Kubernetes configuration as a secret in encrypted form. So this example comes from the configuration from Apache Airflow Helm chart on a very similar basis. Cloud Composer stores also secrets using Kubernetes secrets. Another very interesting feature that Kubernetes offers to is autoscaling. Autoscaling features are characteristic to the specific Kubernetes offering or configuration. That's why I'm going to focus on Google Kubernetes Engine, which is a managed service for Kubernetes offered to you by Google. So Google offers three types of autoscalers for you: horizontal pod autoscaler, a cluster autoscaler, and vertical pod autoscaler. So those autoscalers are used depending on the need of auto scaling. So for example, if your cluster needs more or less nodes in the cluster, cluster autoscaler is going to take care of this task. On this slide, let's maybe focus on the horizontal pod autoscaler. Cloud Composer and Helm-based Airflow installation uses horizontal pod autoscaling to control how many Airflow workers you are going to have in your configuration. The way it works is, if you have a lot of Airflow tasks to be executed, you can ask horizontal pod autoscaler to create more Airflow workers. So those tasks are executed as quickly as it is possible. Once you have smaller number of Airflow tasks in the queue, the number of workers can be scaled down. So in general, the concept in case of Cloud Composer and Helm-based Airflow approach are very similar. There is a dedicated metric that is maintained by special components. In case of Cloud Composer, this component is called Custom Metrics Stackdriver Adapter. In case of the Helm chart offered to you by the community, there is a component called Kubernetes Event-Driven Autoscaling. Those components are maintaining metrics. This metric is actuating horizontal pod autoscaling, and horizontal pod autoscaler makes a decision, okay, I need to add more Airflow workers, or for example, I can remove some workers to save some additional resources. Another interesting feature of Kubernetes are probes, and this is the way or means for Composer to discover if your components of your system running on Kubernetes are healthy. So there is so-called startup probe, and this probe tells Kubernetes whether your component, for example, once it was restarted, whether it already finished initialization. If it didn't finish, Kubernetes know that it needs to wait until the initialization is finalized. Once the initialization is finished, we can use a so-called readiness probe to be able to validate or evaluate whether Kubernetes can start sending traffic to a given component. So, for example, you remember that one of the things that we discussed that, for example, we could have a Kubernetes service for web servers and two pods behind this service. And Kubernetes will wait until readiness probes gives green light to it before it starts sending traffic to Airflow web server pod. Once the initialization is finished and Kubernetes confirmed that the component is ready for accepting the traffic, here comes liveness probe. And this probe is used to pass the information to Kubernetes about the healthiness of the component. So, for example, you could try to discover deadlocks that make scheduler not working properly. Or if Airflow worker is not able to execute tasks, you could also discover it. As a result of it, Kubernetes, once it gets a signal, okay, this component, it doesn't work as expected, it can restart it, and in this way, auto heal it. So, for example, Apache Airflow Helm chart delivered to you by community gives you the possibility to use liveness probe for scheduler. And this liveness probe validates whether scheduler can create tasks. And if it can, it means that it can add tasks to the queue, and executor can pass tasks for execution to workers. On the other hand, if scheduler cannot fulfill this duty, it's a signal for Kubernetes, okay, there might be something wrong with scheduler. Maybe I can restart it, and maybe it's going to help and auto-heal the situation. When it comes to Cloud Composer uses liveness probes for all the components. And here in this slide, you can see a snippet of the configuration of Airflow Worker. Here you can see actually that Airflow Worker has a special file called Worker Checker, a Python file, within which you have a program that validates the healthiness of Airflow Worker. One of the health checks that is done within this Python program is, for example, validation that Airflow Worker can pick up tasks from the queue. And of course, again, if the worker checker passes the information to Kubernetes, everything is okay. Kubernetes does not need to do anything. If worker checker discovers problems, it can gives a signal to Kubernetes to restart the component, and in this way auto-heal the component. So in summary, as you can see, Kubernetes and Airflow married together. Kubernetes is a very rich platform, and it has a lot of features to offer to Airflow. So Airflow, it can be run in a reliable and scalable way on Kubernetes clusters. The features that we focused today on is declarative way of defining components and adjusting workload types to the needs of those components. We can use auto-scaling and auto-healing capabilities to expand or shrink down the cluster to adjust it to the current needs of Airflow configuration, and we can use probes to auto-heal the components. Kubernetes services are used to load balance the traffic and provide a means of providing permanent endpoints for Airflow components. And Kubernetes secrets, this is the way of storing the parameters of Airflow in a very secure way, in the encrypted way. In this way, Airflow configuration is much safer. With that, we came to the end of this presentation. I hope that you enjoyed. I recommend to you trying out Airflow, either by using Cloud Composer or using Apache Airflow Helm chart that is provided to you by Airflow community. If you need to find me, here's my Twitter account. Feel free to drop me a question if you have any. Thank you.
Thanks, Rafał. I know there are lots of different ways to run Airflow, but folks love Kubernetes. It was great to learn more about how Kubernetes and Airflow are a great match, especially with Composer. Okay, that's a wrap. You know what that means. It's time to join us at the after party. You can do so by clicking the Watch Live button on the event's agenda page.
And today's speakers will also be joining us, and we'll have an exciting quiz and follow up some Q&A. We hope to see you all there. Thank you.